Good morning, good afternoon, good evening, everyone. Welcome to our webinar organized by the International Society of Antimicrobial Chemotherapy Early Career Working Group. So I'm Jinxin Zhao from Monash University, Melbourne, Australia. Before start this webinar, I would like to introduce a few information about ISAC and ISAC Early Career. So the International Society of Antimicrobial Chemotherapy, which is aimed to advance the education and the science of the therapy of infections through the establishment of an international federation of affiliated national and regional societies with similar aims and objectives to its own. So currently, ISAC currently has more than 90 member societies and more than 50,000 individual members. If you need more information, so feel free to get in touch. Under the ISAC, there are 21 working group. Our early career working group works closely with the ISAC and other ECR members. Which we basically focus on serving a platform to communicate with senior researcher and providing ECR worldwide opportunities to build long-lasting networks for collaborations. And this is our working group leader team. We are actively working with ISAC and the ECR members to propose programs and events for the ECR community. If you have any idea and interested, have any interest, feel free to join us. So today's webinar will be the third webinar of the webinar series on when pharmacometrics and system pharmacology meet infectious disease. And before we start, I also would like to give a short advertise about our next conference, the 33rd International Congress of Antimicrobial Chemotherapy, will be held in Istanbul next year, November. And if you have any exciting results, feel definitely submit an abstract and go for this one. Yeah, so I will introduce our moderator today, and Wenyi Li. Dr. Wenyi Li is a lecturer and a lab head from La Trobe Institute for Molecular Science, La Trobe University, Australia. He has successfully secured multiple very competitive grants and fellowships in Australia. So I'll hand it to you, Dr. Wenyi Li.
Thank you, Jason. Yeah, so it's my great pleasure to moderate this webinar, which will given by Dr. Meiling Han. So Dr. Meiling Han is currently is a group leader at Monash Biomedicine Discovery Institute at Monash University at Melbourne. So she has won a number of awards and fellowships. She currently is holding Australian Research Council DECRA earlier career DECRA fellow. So she is her research areas mainly working on using different techniques to trying to study the membrane lipid with antibiotics in gram-negative bacteria. So today, she will give a talk about the membrane lipid remodeling conference, polymyxin resistant in gram-negative bacteria. So if anyone have any interest, and so we can put the questions in the chat or Q&A, so we can put the question in the end. So Meiling, yeah, so would you like to start? So yeah, thank you.
Hello everyone. Thanks, Isaac, for this great opportunity to share our mechanistic studies on polymyxin resistance. Today, the title of my talk is Out-membrane lipid remodeling confers polymyxin resistance in gram-negative bacteria. So as we all know that antimicrobial resistance has become a major global threat for public health. If unchecked, AMR will cause estimated 10 million deaths per year by 2050. In fact, in 2019, AMR has already caused 1.27 million deaths globally. Therefore, WHO has listed AMR as one of the top 10 threats, global threats for public health, and published a list of priority pathogens. In this list, the gram-negative species Acinetobacter baumannii, Pseudomonas aeruginosa, and Enterobacteriaceae are the top 3 critical pathogens which urgently require novel antibiotics. Unfortunately, over the past 3 decades, the number of FDA-approved novel antibiotics has been significantly declined. So without novel antibiotics, we use the one of the older class of antibiotics, polymyxins, as the last line therapy. Polymyxins are a class of cyclic lipopeptides which contain positive charges and mainly target the out-membrane of gram-negative bacteria. So just because the importance of polymyxins, our lab has been significantly focused on the research of polymyxins over the past 20 years. Our research is mainly involved in these 3 streams. Through clinical translation to optimize the use of polymyxins and combinations in patients, and through fundamental research to study the mechanisms of polymyxin activity, resistance, and toxicity, and also through commercialization to discover polymyxin novel antibiotics, phage therapy, and formulations. My research is mainly involved in the mechanisms of polymyxin activity and resistance. Polymyxin activity is primarily associated with the interaction between the positively charged polymyxins and the negatively charged lipid A, which belongs to lipopolysaccharides in the out-membrane of the gram-negative bacteria. Just because of this, the bacteria are able to remodel their, modify their lipid structures to resist polymyxin treatment. Lipid modifications mainly include the charge modifications and hydrophobic modifications. In addition to this, some bacterial species, including the Acinetobacter baumannii, may survive polymyxin treatment by totally removing their LPS. So how do bacteria generate lipid modifications? It is known that the 2-component regulatory systems, 4PQ and PMR-AB, are responsible for lipid modifications in most gram-negative species. And the conditions of low magnesium, low pH, or the presence of antimicrobial peptides, such as polymyxins. The inner membrane kinase 4Q will be activated. This will phosphorylate 4P and then activate the PMR-AB regulatory system through the gene called PMRD. This activation will upregulate the ARN operon, which is responsible for aminoarabinose modification, or the upregulation of PMR-CAB operon, which is responsible for PTN modification. In addition to this, the 4PQ system itself could also regulate the upregulation of PEG-L, which is responsible for lipid A deacylation. There are some other lipid modifications, including lipid A phosphorylation, modifications to the sugar unit of LPS, or another lipid deacylation format are also regulated by these two regulatory systems. Okay, as lipid modification is the major mechanism for polymyxin resistance. So my study was firstly involved in lipid modifications in Pseudomonas aeruginosa. This is the workflow for lipid analysis. In this study, we employed a pair of Pseudomonas aeruginosa strains, the polymyxin susceptible PAK and the polymyxin resistant PAK-PMRB6 strains. We used the mild acid hydrolysis method to prepare lipid A. This method is to break down the sugar units from the LPS structure, and the lipid A structures were analyzed by the mass spectrometry analysis. In the analysis, we found that the wild-type strain produced the unmodified lipid A, including the pentaacylated and hexaacylated lipid A. While in the polymyxin-resistant strain, these lipid A were modified with 1 or 2 amino arabinose groups. We also quantified the dynamic change of lipid A in both strains and the polymyxin treatment. We found that polymyxin treatment only induced the generation of amino arabinose modified lipid A in the wild-type strain. However, in the polymyxin-resistant strain, polymyxin did not induce extra lipid modification, as this strain already produced a very high level of amino arabinose modified lipid A. In addition to lipid modification with amino arabinose, we also found that polymyxin treatment could induce lipid A deacylation, with the deacylation level significantly increased after polymyxin treatment across 24-hour period. Consistently, the expression level of PEG-L was significantly increased in both strains after polymyxin treatment at both 1 and 4 hours. We then deleted PEG-L from both strains. However, we found that the deletion mutant of the polymyxin-resistant strain showed increased polymyxin susceptibility, but not the mutant of the wild-type strain. This indicated that compared to lipid modification with amino arabinose, which is the primary mechanism for polymyxin resistance, lipid A deacylation was a secondary mechanism for polymyxin resistance, which may contribute to high-level resistance. Okay, to fully understand the polymyxin resistance at a network level, in addition to lipid modification, we also focus on bacterial lipids, metabolites, and genes. So the next study is about metabolic pathways associated with polymyxin resistance. In this study, we used the integrative transcriptomics, metabolomics, and lipidomics to study the essential genes, metabolites, and lipids responsible for polymyxin resistance. Using integrative multi-omics, we found that polymyxin treatment was largely associated with the perturbation in pathways related to bacterial cell envelope biogenesis. This is the pathway of lipid modification with amino arabinose. Using quantitative metabolomics, we found that the metabolic levels of essential intermediates were significantly increased in the wild-type strain after polymyxin treatment. However, in the polymyxin-resistant strain, which already produced a very high level of these metabolites, polymyxin treatment only slightly increased their levels. Our transcriptomics data produced provided very consistent and similar gene expression pattern. This data together suggested that polymyxin resistance was not only related to the genetic mutation, but also the metabolic and transcriptomic perturbations. Our data also showed that polymyxin treatment could significantly affect the metabolite levels associated with LPS and cell wall biosynthesis made in the wild type strain, but the resistant strain also showed a similar trend. In addition to lipid A modification and LPS biosynthesis, we also analyzed the perturbations in other membrane lipids, including the phospholipids and fatty acids. And we found that polymyxin treatment significantly affected the levels of membrane lipids, especially a class of lipoamino acids, which are significantly increased after polymyxin treatment in both strains. The increased level of these lipoamino acids may contribute to stabilizing out membrane by counteracting the negative charge of LPS and potentially confer polymyxin resistance. In addition to the perturbations related to membrane lipids, our study also showed that the metabolite levels associated with methionine salvage cycle also significantly changed in the two polymyxin-resistant strains compared to their parent. This pathway is also related to spermidine biosynthesis. Due to a stop-gant mutation in SPE in one of the polymyxin-resistant strain, we found that the level of spermidine was significantly decreased in this strain. It has been reported that spermidine may contribute to polymyxin resistance. This could explain that why this polymyxin resistant strain showed a lower resistance compared to the another polymyxin resistant strain. Moreover, our data also showed that polymyxin treatment could significantly upregulate the gene expression levels of SPED and E, which SPE encodes spermidine synthesis, significantly increased in the wild type strain. So in summary of this section, our study has shown that the polymyxin killing and resistance are largely associated with LPS synthesis and modification, cell wall synthesis, spermidine synthesis, and lipid metabolism. In addition to this, we also showed that polymyxin treatment could affect the central carbon metabolism, virus transport, and sulfur transport. This metabolism require further investigation for their exact role in polymyxin resistance. So in the second part of my presentation, I would like to talk about another mechanism of polymyxin resistance, which is due to LPS loss in Acinetobacter baumannii. As I mentioned from beginning that many Acinetobacter baumannii strains may survive polymyxin treatment by removing their LPS. This will result high-level polymyxin-resistant strains. From these LPS-lost strains, we recently identified an interesting phenomenon that many strains could not grow on normal agar plates without the presence of clistin. This is also the case in the liquid medium, that the presence of polymyxins could enhance the bacterial growth. We call this phenomenon polymyxin dependence. So to generate polymyxin dependence, a primary step is to lose LPS by inactivating the LPS biosynthesis pathways, particularly by inactivating the genes in the first few steps. In our polymyxin-dependent strain, we found an insertion in the LPS-C gene. The complementation of LPS-C in the dependent strain completely lost their dependence. We also found another mutation in the gene CATG, which encodes peroxidase. And the complementation of this gene partially lost the dependence. This indicated that the dependent strain may face severe oxidative stress. With integrative transcriptomics, metabolomics, and out-membrane proteomics, we have identified that polymyxin dependence was largely associated with perturbed membrane biogenesis, including lipid A biosynthesis and modification, lipoprotein trafficking, peptidoglycan recycling, and lipid metabolism. To further study the membrane perturbation, we developed a method called membrane lipidomics. In this method, we used the sucrose density gradient with ultracentrifugation to separate the inner and outer membrane fractions. The separated membrane fractions was normalized based on total protein concentration quantified by BCA assay, and then lipids will be extracted from the membrane fractions and analyzed by LC-MS. For data processing, we used the MS spectra for lipid identification and the authentic phospholipid standards for quantification. The targeted lipid screening was processed in a software called TraceBander. Using this lipidomics approach, we found that the proportion of major membrane phospholipid, phosphatidylglycerol, was significantly increased in the dependent strain compared to other strains, including the polymyxin susceptible strain, polymyxin resistant strain due to lipid modification, and the LPS lost strain, but not dependent. The complementation of CATG or LPS-C decreased the levels of PG. Next, we wonder if the increased level of PG is related to polymyxin dependence. So using this lipidomics data, we constructed a membrane model for the dependent strain using molecular dynamics simulation. And we found that clistin could decrease the membrane diffusion. Moreover, our data also indicated that only when the PG proportion increased to 35% and above, clistin could decrease the membrane diffusion. This could explain why this strain, the 5075, showed dependence. but not the another LPS lost strain. Our data also shows that the PG-rich membrane of the dependent strain formed more hydrogen bonds with cysteine. This indicated a stronger interaction between the out membrane of the dependent strain with cysteine. So with the presence of cysteine, the membrane of the dependent strain was stabilized. So this could decrease the influx of hydrogen peroxide and then decrease the generation of hydroxyl radicals. That's why the bacteria grow better with the presence of polymyxins. I think I ran a little bit faster. Here are some take-home messages that you can clearly see from my talk that membrane lipid remodeling is critical for bacteria to resist cationic antimicrobial peptides, and the intracellular metabolic pathways are also associated with polymyxin resistance. And we can also see clear crosstalks between them. And in the last part of my talk, I showed that arginine metabolism could be a target to improve the diagnosis and the treatment against the invisible polymyxin-dependent bacteria in patients. My research is involved in integrative multi-omics biophysical and computational approach, which is critical for the mechanistic study of membrane targeting antimicrobial peptides. Okay, so with that, I would like to acknowledge our group members, our collaborators and funding bodies, especially my mentor, Jian, my collaborators, Tony, involved in my biochemistry study, Trevor Reese involved in the bacterial membrane separation, Chris, Scott, David, and Darren involved in metabolomics and lipidomics studies. Xinhui and Anton involved in my neutron reflectometry studies. Samuel and Alina involved in PEG-L deletion. And thank you all for listening. I'm looking forward to your questions.
Thank you very much, Meiling. Very impressive journey of the polymyxin metabolism study with the membrane interaction and their target lipid A. So there is a couple of questions from the chat. So the first thing is there's the question is asking the polymyxin resistant is that can that attributed to some genetic factors for those resistance?
Yes, yeah, of course, polymyxin resistance is usually attributed to the genetic factors, including some adaptive genetic mutations or some intrinsic genetic mutations. Sorry, I'm not a microbiologist, so probably not a perfect person to answer the question, but based on my understanding, such as recent plasmid-borne the mutation, the gene called MCR1 also could cause the very significant polymyxin resistance. Yeah, I think this is a very common, very common sense that polymyxin resistance can be attributed to genetic mutations.
Yeah, and also I have a small question, because the first part you also showed that there is some the lipid A and the wild type, and also the resistant type has been, the lipid A has been modified then. So yeah, in that case, so in generally the report has showed the major target for polymyxin A. Polymyxin, and their target is lipid A. So after their modification within the resistant strains, is the binding affinity are still maintained the same, or that binding with the modified lipid A is contributing to their activity, the loss of the activity?
Yeah, that's a great question, Wenyi. Of course, the binding affinity has been significantly changed due to the lipid modification, and modification could significantly decrease the binding with clistin. As we can see that the binding between polymyxins and lipid is mainly due to the charge interaction, due to the positive charge in polymyxin and negative charge in lipid A. When the lipid modification occurs, especially due to the charge modification, the negative charge in lipid A could be blocked with positively charged sugar units such as the amino aeruginose. And if no negative charge in lipid A, the binding will be significantly decreased. That's why the resistance is being generated.
Okay, yeah, it's very nice. And there's another question is coming is asking is the did polymyxin dependent strains that show dependence to other antibiotics, or have you done this, or what's your thought on this?
We have tested. Yeah, we published the paper. We have tested the dependent strains with other antibiotics, and the dependent strains showed increased susceptibility to other antibiotics, including like daptomycin or vancomycin, but not dependence to these antibiotics. We tested polymyxins, the cyclic polymyxins or the linear polymyxins or other polypeptides, and we found that the dependent strains could only show the dependence to polymyxins regardless it's cyclic or linear, but not to other polypeptides.
Yeah, okay. Okay, so I have a question here following up this question. So for those because those strains that you have showed is the polymyxin dependent strains. So do you think or do you know, or have you ever seen any other bacterial strains that have a dependence to other antibiotics? The question I'm asking, the question I'm asking here, because you also later on showed the polymyxin is remodeling the membrane, because polymyxin is mainly targeting the membrane of bacteria. But for some other antibiotics, they are not mainly targeting the membrane. They have other targets. So what's your thought, or do you know what have any people study the mechanism of those dependent to other antibiotics?
In the literature, it has been reported the dependent strains to other antibiotics, probably not like Acinetobacter, baumannii strains, but other bacterial strains show the dependence to other antibiotics. But I haven't seen the mechanism being clearly elucidated. So as you said, probably like other antibiotics may not target the membrane. So sorry, I'm not very sure about the exact mechanism. Yeah, but and also for us, we are also analyzing the like other bacterial species like Neisseria, because it can also lose their LPS to generate polymyxin resistance. So we are also analyzing this bacterial species and see if their LPS loss strains show the dependence or not.
Yeah. Okay. Thank you. Very nice. So there's another question is coming up asking about the prevalence of the resistant in populations. So do you know, do you have any comments on what is the prevalence of the resistant in population? I guess is in specific bacterial population?
Yeah, I think it depends on the bacterial species, right? Yeah, I have seen a figure that I think I can. I'm not sure if I can find that figure right now. Probably not. Sorry. I think for the prevalence of the resistance in populations, the polymyxin resistance is still in low prevalence. Yeah, but I can't. At the moment, I'm not able to tell the exact like the percentage or the prevalence for polymyxin resistance, but as I understand, it's still under low prevalence. Yeah, that's why we still stick to polymyxins as the last line therapy.
Okay, yeah, and that's very related to the next question, which is
okay.
So if polymyxin is resistant to baumannii, so and which next antibiotics should be used? So as we all know, polymyxin is the one of the last resort. So
yeah, that's why in our lab we aim to discover novel antibiotics, not only the novel antibiotics belonging to the class of polymyxins, but also other antibiotics. For polymyxin discovery, we have developed novel polymyxins showed increased. We modified the some groups in polymyxin structure, like mainly the hydrophobic groups, to increase its activity, and also our novel polymyxin analog also shows the decreased toxicity. So this is one of the options, and for other options, we may consider other like membrane targeting compounds, such as the Enterobacter. That's one of our chemists in our lab. Jinxin has been doing for quite a long time, and also like some phage therapy, which is very popular at the moment to target some antibiotic-resistant bacteria.
Yeah. So one last question from chat, which is about the So do you know is any the role of the polymyxin be resistant about the overexpression of the efflux pump system in the gram-negative system, gram-negative bacteria?
Yeah. We have seen we did many transcriptomics studies with polymyxin treatment in different gram-negative species, and we continually see the upregulation of some efflux pumps, like I can't clearly recall the name of the genes, but these are the membrane proteins that belonging to the efflux pumps. We can see the increased expression of these genes. We in our lab we haven't tested the role of these efflux pumps, but I know some groups some groups they have found the sort of role of efflux pump in polymyxin resistance, but probably not that exact. The role maybe not that clear.
Yeah. I can follow up with this question. Like I think from our group, like for polymyxin resistant from the transcriptomics or study, we basically we mainly the main finding for those like differentially expressed gene is ADE efflux pump. So it's ADE ABC cluster. And there's one study last year or the year before published by Professor Catherine Holt, and they isolated a clinical isolates and did the comparative genome and found like there's a ADEN, which is a suppressor of the ADE ABC operon, and basically there's a insertion there. So inactivation of that gene is a kind of overexpression of the downstream ADE ABC cluster, and also it could be some missense mutation happened in the ADES, which also can cause the overexpression for the downstream or the ADE ABC. Yeah.
Thank you, Jinxin.
It's just coming up another very good question about phage therapy. I think it's currently is in a hot topic for the phage therapy for AMR study. So what's your point of view of the phage therapy to combat the multi-drug resistant bacterial infections?
Thank you for the question. Probably I'm not the best person to answer this question, because I did some phage study and published a paper using the using metabolomics to study the metabolic changes responsible for phage therapy, and I think it's a promising option to study further for phage therapy, like the phage cocktail, to minimize the generation of the resistance, and also probably we need to think to enlarge the antimicrobial spectrum. That's one of the limitation. Probably Jinxin could help me to answer more about this question.
Yeah, I think sure. Phage therapy definitely a very hot topic nowadays, and the only thing is we need to carefully consider the usage of phage therapy, especially the PK profile of phage therapy is very complicated. And we definitely need to think about a method to optimize the the dose of phage, and how to translate this to the clinic. And this could be found. One of the ways using PKPD modeling, which already has been introduced by Dr. Wenyi Li at our first webinar. And if you want to get some information from the PKPD modeling, definitely go with that one. Yeah.
So thank you, Jinxin.
Sorry. Actually, following this one, I actually have a question for Wenyi. So, cause I saw the question people ask what kinds of next drug we should be used if most gram-negative bacteria become resistant to polymyxin. So as an expert in peptide synthesis or peptide chemistry, how I just want to know how difficult to develop a pure a novel peptide, antibacterial peptide, and to make it really happen from the laboratory and to the clinical practice.
So I think also thank you, Jinxin. I think also associated with the question in the chat, it's also asking any other new method to develop the new antibiotics. I think that's a big question. I just give some point of my point of view. It's probably not the best answer. So peptide antibiotics is just one way to trying to develop developed a tool to combat the bacterial resistance, and like the previous question, phage therapy, and also some people was trying to using antibodies or specific to modulate the immune system. Yeah, so I think it's challenging. But it's also a promising field as well, because the bacterial infections is a big issue, and especially it's COVID, put a big alarm there, and then it's a kind of a silent pandemic for us. So from lab bench to real clinical field, I think the definitely Meiling the Professor Wenyi Li, they have done a lot of work on polymyxin, and that's probably even for me, I have heard that it's not 5 years, more over 10 years, or even more than 10 years way to develop a new drug, which is in clinical trial, not in the end, and really in the market. So I think I think there's a lot of work we need to do, and polymyxin is one way, and for us, the way mainly working on an antimicrobial peptide, which is another way. So and also there's a lot of experts in this field, so we are doing some small part of the work, trying to not only developing some peptide directly targeting the bacteria, but also can modulate the immune system. So with a dual functional peptide molecular as another tool. So I believe there is definitely have a lot of potentials. Definitely is I think COVID has taught us is the very collaborative environment. Definitely will make something happening very soon, very fast. So like the mRNA vaccine, or how we never thought those vaccines can develop in such a short time. So when we really need something, and so I think there's definitely have a lot of ways to push this forward. So I think that there's a lot of potential in this way. So definitely it's the more collaborative work, and also like to share, like the Isaac those webinars to share the knowledge with each other. I think it's definitely will helping us to give a bit of more potentials, and to know what others people have tried as well. So yeah.
So actually one question is asking, is Dr. Meiling Han open for collaboration?
Yes, of course, for sure. Yeah, without the collaborations, how could I manage such a comprehensive projects? Yeah, for sure. I'm always welcome for any collaboration. Yeah. So if you have any collaborative projects, or you could contribute to our projects. So please, you can approach Jason for my contacts. Yeah, if they haven't posted in the ISAC webinar.
Yeah, thank you.
Yeah, thank you.
I think, thank you everyone. So it's hope everyone have a good day, good night. Yeah.
Yeah.
Okay.
Thank you.
Thank you all. Thank you.
Bye.
Bye. Bye.